right, I think it's time to get started. So gather around, move up a little bit if you want. If at any point you have questions or remarks, just shout. Will be fun. Road to Reactive with RxJava. I'd like to begin with legacy. Legacy is a beautiful word. Normally, when you talk about legacy, you talk about beautiful things, things you did and will live on in history when you're long dead. So you have all kinds of classics that are legacy. And even if you look a bit more to the modern times, you get to like classics like this car, which is a beautiful car. And even though you could say that if you have a car now, you could say, oh, my 2013 Toyota is a better car than this, which is true, but this is a classic, and this is a thing of beauty, and it will remain that way forever. Software is not so lucky. Usually we don't really look that fondly back on old software. We think, oh man, that was so great. So we have a few classic pieces of software, I guess, something like this. Will just make people cringe a little bit. This one, even worse, from the time that internet nearly worked. The only one that gets a really kind of reaction is this one. That takes you back, but it's more sentimental than being truly classic, right? So, why don't we love old code, right? What's wrong? But maybe this comparison to the classics of the world is not really fair, because software and software we use, we constantly move the bar. We constantly wanted to do stuff that it didn't do before. Like if that classic car runs the same way it did 40 years ago, you're a very happy guy. If your software works exactly like 40 years ago, you're not going to find that acceptable. So I would like to make a different comparison and comparing software to perhaps a city. This is my hometown of Amsterdam. And a long time ago, well, not really long time ago, in the 60s and 70s, there was one neighborhood about here. And that neighborhood wasn't doing too great. That neighborhood, the buildings were kind of in disrepair. And because of the soggy soil in Amsterdam, buildings start to tilt. So you need to prop them up in all kinds of ways. People who could afford to leave left, and the people who were forced to remain were poor, and it was just not a nice place to be. It was a kind of a Dutch Detroit in a way. So at some point the governor thought, we can't fix this anymore. We're going to tear down the whole thing and rebuild it, and it will be great. Well, it never happened. There were a lot of protests, and people started to just refuse to leave, squat in empty buildings, and so it never happened. So that is good, because it started to go up after that. People started to renovate houses, it started to get better. Now it's a really pleasant place to be. It's one of the most in-demand places in the country now. And even though the decision to tear it down was a very sensible thing to do. I mean, if you can't fix it, replace it, yeah, sure. But now it's a really nice place to be, and I think we dodged a bullet, because the stuff they built in the 70s was horrible. It was like boring at best and complete ghetto at worst. So we dodged the bullet. It was a good thing it never happened. So if I get back to software a little bit, throwing away old code is really tempting. It's a really nice idea to start with a fresh slate and throw away everything you got, because then you also throw away all your technical debt. You throw away all your design decisions that turned out not to be that great. There are a lot of, you can fantasize about how everything will be great once you have that new framework you just heard about. And I think many technologies are actually kind of preying on that. They say, look how easy it is to make something new and shiny. But in the end, you might very well end up in the same place you started. So actually, it's a trap, right? You can start over again and expect things to change, but it won't. You will have slightly new problems, but usually you get the similar shit if you don't really change your ways. So replacing legacy systems turns out to be really hard, and it's also often not that satisfying, because it's nice to start new, but in the end, there are a lot of things. You probably go really nicely at first, and once you hit 80 or 90%, then it starts to get hard. And if you need to replace something that's in use by users, users will only complain because it's not the same as the old system, which was kind of the point, but you know what I mean. So actually, the projects to replace legacy systems are one of the worst performing projects, even though it's a pretty straightforward thing. You have something that works, you rebuild it in a new way, and you know exactly what you're doing. But it seems not to really work that way. It seems to be harder than it looks. So, but the problem is we are building a lot of software, and we can't keep on expecting every software to be replaced every few years, because there's simply too much of it. So what I want to say here is, love your code like your hometown. Don't let it rot. If there's something broken, fix it. If it's no longer relevant, replace it. But don't expect it to throw it away, because face it, we are going to live in a world full of old software, and it's going to get worse. So that was my intro about me. I'm Frank Lyaruu. I'm from Dexels. I'm specialized in enterprise software for sports federations in the city of Amsterdam. One application I've been building for 13 years now. And this is when it started. It was a Java servlet on top of Oracle database. Those were the simple days. Right now, it's a bit more confusing. There's a lot of things in there, but it is, for all intents and purposes, it is the same application. And to me, I really like the fact that it has so much history. It's so much more interesting to have to work with all this history than when you have a greenfield application, which is kind of, in a way, the same every time. So, but to get a little bit more to the point, blocking code. We all know blocking code, I think. You know blocking code? You don't know blocking code? Yeah, okay, that kind of question. So, for example, blocking code, you do something, you get a response, and after that you can do something else, right? So that's how blocking code works. You do stuff, you end with a nice semicolon in Java, and then you go on and on. So, straightforward, right? That's how we have been working for forever. So it is one big advantage is that it's easy to compose, right? If you want to do one thing and you want to do another thing, well, you do one thing, then the other thing. Easy. It's easy to reason about, right? It's you can talk about where you are in the code. You have like a point of view. This is I'm at that line. It's pleasant to debug. You can put a breakpoint there and then check if it is what you expect. You can make log statements. It's all really pleasant. It also maps nicely to like low-level assembler instructions. It's often efficient, not always. It's extremely mature, but most important of all, it is familiar. There's no way around it. I mean, I showed the Commodore 64 screen. I have been coding blocking code since then. So I think many of us have a lot of experience in blocking code. So it might be that at some point we start believing that that's the only way to do it. And that's not true. So blocking code looks pretty good, right? If we look at this, because yeah, a lot of nice aspects. And why should we mess with it? In many cases, the answer might be, don't, it's fine. But not always. One thing is that blocking code is only efficient when it's actually doing something. It's not efficient when it's waiting for something. That's something that blocking code really can't do. You can't really express that in that way. So another thing is that because it can't do that, you use a lot of threads. And threads are expensive at scale. They're one of the most rare resources on a server nowadays. So, for example, if I do a remote procedure call, I could do some, I don't know, some RMI call or, God forbid, a SOAP call, but some kind of remote call. And if we zoom into what this thing will actually be doing, if we think about it, it will create some HTTP request. It will try to shove that through the network connection. That will probably take forever from a thread point of view, because threads are fast, but networks are slow. It tries to do it. At some point, it's done doing that, and then it starts waiting. And it sits there staring at that socket for something to arrive. And that can be, if it's fast, it's a few milliseconds. But for a CPU thread, that's an eternity. It just sits there. And that's a big waste, right? And if you have a system which is a lot of these calls together, it might very well be that 95% of all your threads are sitting there staring at a socket. So that is a problem. This is a nice illustration. This is, I'll just do this one, for example. I can't really read it. But it does 3 reads to a HTTP client, to eBay, I think. It searched for mouse, beer, and gnome. This is the blocking one. So this is the thread. It starts the connection. It waits for it to finish. At some point it's finished. It starts the next one. Finish. Start the next one. This one, the one on the bottom, is an asynchronous one. So it will pipeline all the 3 connections. It will push it through the line straight away. And then the server will be listening to those 3 in a row. And then it's non-blocking. So when in the green part, the threads are actually free again. They can do other stuff. And if you look at the numbers, that's pretty amazing, because like it's only doing something for 1 millisecond. And then it's doing nothing for 500 milliseconds. So this bar is shorter because it does more at the same time, which is nice. But the more spectacular difference is how much more threads could do if only you don't have them sitting around staring at sockets, right? So, it gets worse. Microservices. Microservices are very popular and very nice from architecture point of view, but it means that you have often code which connects to other systems all the time, right? There are so many systems now, and it's connecting. If you, so at any time, if you call to another service, that service might call to another service, and maybe one piece of code might not be blocking 1 thread, it might be blocking 10. So at scale, it gets really, really expensive if you use blocking code. It gets worse. So slow network connections, so when the network is slow for whatever reason, that's really expensive because, as I said, threads on a server are expensive to have. It's a very rare resource. But, for example, if we use mobile devices as clients, they can be slow. It can suddenly happen that it goes silent for several seconds, right? And all the time that poor thread is waiting for something to happen. So it is much worse if you have mobile connections. And also, if you have some kind of performance problem in some corner of your system, it will spread. Because like it will cause more threads somewhere else. Those cause more threads to be open, and that will be in a loop. And at some point, the whole thing will burn down. And at some point, and you can't really tell what caused it, because the thing that caused it might be completely fine, but the rest is all smoke and ruins. So generally, if you have a big blocking system, when it gets overloaded, it doesn't do so in a very graceful way. So blocking code is at scale expensive and a liability for distributed systems. And distributed system, that's nowadays is any system, right? So we need to face that we have to do some non-blocking code at some point. So if you take a very short and non-scientific way of looking at what is non-blocking code, it's basically that the method will return before it's really ready. It's kind of ready. So if I write to a socket, I put some bytes to the socket and I say write this, and it will say okay. It might not be done, but it's kind of committed, and at some point it still might fail. I don't know it's done. So if it returns without an error, that means absolutely nothing. That it doesn't mean it's done. It doesn't mean that it will succeed. It might do nothing at all. So that opens up some questions, right? So when will it be finished? How do I know if it succeeded? And this is the last one is a very often forgotten one. How hard can I hammer this thing? How often can I call this? Because if it's still doing something, it might get some backlog, but you don't really can tell. So often we fix this by callbacks. Kind of classic. I'm pretty sure we've all seen them. You add some kind of callback routine, so use a nice lambda or something, and that will be called when it's done. And it's not too bad. It works. We do it all the time, especially in languages like JavaScript, but increasingly also in Java. And it kind of works until you have a lot of instructions, because then you end up with something like this. You do one thing, you have a callback, and in the callback you do another thing, and that has a callback, etc., etc. And this is what we call the pyramid of doom. Because you end up with a piece of code and it ends with like 25 brackets, and you have no idea where you're at. And before, when I talked at blocking code that we can use semicolons to compose code, we can't do that anymore. This one is here because Java likes it, but it's kind of meaningless. But we can't put instruction next to another anymore. And that's a kind of a loss, because we can't really have a graceful way of composing code. So now I would like to talk about an example. Servlets. Who has used servlets? Excellent. Who has used non-blocking I/O of servlet 3.9? Some hardcore people. Good, 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 good. So I started with a blocking servlet. And this is an echo servlet. So you put something in, like put or post or something, and it will return that. It's kind of the hello world of servlets, right? So it's pretty straightforward. You have a bit of a buffer. You loop around. You read what's coming in, and if it's nothing to read anymore, you break and you write whatever you got. This is quite easy to understand, this piece of code. If I go to the non-blocking variant, it's a bit less pretty. This is this is painful, and it's actually worse than it looks. It's impossible to figure this one out. And this is not a hack job by somebody. This is really smart people really thought a lot about that API, but it is just complicated. So I'll show a little simpler example, because then we can at least read it. Here I try to read a file and I write it to the output stream, like a get or something. Now, it's a lot more complicated than the blocking one. So what happens here, I'll not dwell on it too long. I attach a write listener to the output stream. So then I will say to the output stream, you are in a non-blocking mode now. Actually, it's not an output stream anymore the moment I do that. That's kind of a mindfuck, but still, that's the case. So whenever the servlet engine knows that there is room to write to the output stream, it will call you back with on write possible. Then you can write to that output stream, but only once. You can write once. After you write once, you have to call isReady. IsReady might say true or might say false. If it says true, you can write again. Then you have to call isReady again. If isReady says false, you need to return, and then the container will schedule a new on-write possible whenever it is possible. It's not terribly difficult, but it is, but this is the kind of things you need to do non-blocking code in a threaded kind of environment, and that's not really all that pretty. This needs to be different because this is like the hello world, and if it gets any actual complications, then you'll be completely screwed. So blocking code and I/O really does not play nice. So why? Why? Threads are good at doing things. Like you have like a recipe, do this, do this, do this. This is not about doing things, this is about responding to something. So the thread can't make a network move faster, it can't pull harder or push harder to make stuff happen, it just has to be there. And I/O is reactive by nature. You can't, and even if you're local, you're reading from disk, the thread can't make the disk spin any faster. So you need to be reactive to deal with that. Now, this might be shocking. Stand by. This is Node.js, the same thing. Non-blocking. And that makes me a bit quiet and a bit sad. Because this is basically the same thing. It says request, pipe, response. And that's so much easier. It's so much more intuitive to think about it like that. Not with all the, oh, it is ready and then write and then read. No, pipe. Whatever comes in goes out the other way. So a pipe. This is a pipe, right? It's a simple thing. It's a hose actually, but it's something like that. And if you describe how does this contraption work, you would not say like, oh well, it takes a little bit of water on this side and then start transporting, then it takes another bit of water. No, it's a pipe. It is. It doesn't do. So a pipe is like a declarative thing. You say, let there be a pipe, and that pipe pipes. Yeah. So that's a much simpler metaphor here. So, and that's basically what reactive programming is. Programming pipes, putting pipes together and let them do their thing. Reactive X, anybody heard of it? Used it? Did you go to the other RxJava talks? Okay, so it's a polyglot API, so it's many languages, .NET, Java, PHP, Swift, a lot of different things, but they do have the same names. And but obviously, I will focus on RxJava right now. It is similar to the Java 8 streams we talked about before. There are some fundamental differences. I'll get back to that later. But if we talk about the pipes, the words, the source of data is an observable. The destination is a subscriber. So that's basically the words that are used throughout all those languages. So if I have an example here, I have a completely blocking static list of 4 cities in Africa, and that's like the source. So it will create the source that will spit out 4 strings, right? So this basically hands you a pipe here, and this will emit 4 strings. Subscribe will take those strings and print them to standard error, like here, right? So that's basically what we do. If we can also use a range. So we can say make a range from 0 to 1,000 and subscribe that, and then it will just do that. Very basic, very much the same as the Java 8 streams. You can do also some fancy things, well, slightly fancy. You can say skip 10. So then the pipe will say, okay, I'm not interested in the first 10, so the first 10 I will just throw away. After 10, I will start passing it on. Then this one says, okay, I'm only interested in 10. I will pass on 10, and after that, I'm done. And then it will stop at 19 in this case. What's interesting here is that it actually won't put 1,000 items in here, because the take 10 after it did 10, it will say, okay, I'm done. I will tell the piece of pipe before me that there's nothing happening anymore, so this one will pass on the unsubscribe, and at some point the observer will say, okay, nobody wants it anymore, I'll stop doing this because nobody needs it, right? Another one, and this is an interesting one because this is not something the Java 8 streams can do, an observable with an interval. So this will spit out an event every second. So it will just keep on spitting out. I think it gives a number. It gives a long, I think. But often you're not really interested in the number. But that's where the difference with Java 8 comes in. Because in Java 8, you always pull. You pull the data. And here it pushes the data. So this thing is doing absolutely nothing. And from time to time, the observable interval would just throw in one of those items. But there's nothing blocking for the rest. You can do it in Java 8 streams, but then you will have blocking code. So if I would, for example, want to parse something from a file, for example, I have an XML file. I have an XMLified asynchronous parser. This will just spit out pieces of bytes and pass it on to the XML parser. The XML parser will read those pieces of bytes and convert it to XML events like start element and end element. So right here you have like start document, and then you have start element, etc. So now it is converted to a stream of XML events. So we can make it a bit more fancy. So we can parse it, but then we can say we are only interested in the start element types. So the rest will be dropped. And then I say, okay, now I'm only interested in the name attribute of those start elements. So now it's a stream of strings, and then pass it on to the system error, and then you get just the names. For example, you could also do something like this from JDBC. You can, from a database, do a selection, pass a parameter. Although JDBC is a blocking API, and you can't really make something non-blocking. So it won't really help you a lot in terms of performance, but it is still a much nicer flow of code, I think. So if we do this part for the non-blocking servlets, so for the source and for the sink, basically. So this is the read part, and this is the input part, this is the output part. Then, in a way, if we put it together here, we have our Node.js pipe, basically. And this is actually quite a powerful item. I'm not going to show you the gnarly code that's behind those two methods, because it's basically just as bad as the one before, because that's the way it is. But it is possible, and once you have this in place, you don't really need to look there a lot. So I think that's an immediate improvement. So you can have also, for example, the database drivers that have already natively a reactive driver. So this is, in this case, MongoDB, and that is a non-blocking driver, not like JDBC. And then I can, for example, query a database, I get a collection, and then I start just fine, so I just take anything, and it's completely fine if there are like 1 million rows in here. It's completely fine. And then it will write it to the output. And the beautiful thing here is, and that's something you might not realize, is that if this database is slow for whatever reason, it's completely okay. This one doesn't care. So occasionally some data comes in, some more data, then it will just write it to JSON and write it to the output. And if it just does nothing for a minute, it's fine. It's not that bad. If you do it can do like hundreds or thousands of these requests at the same time, because it's basically just a connection. If you have a blocking code, then everything will have a thread blocked, and that makes it so much more expensive. So another one. So I can combine those things. So this is basically the servlet and with the XML parser. And because often we are in the situation that we have some blocking code, right? So if we have a servlet that exists now, but we want to improve it that it will have the properties of a non-blocking servlet, but we don't want to rewrite all the code, right? Because that's a lot of work. So what you can do in this case, I do the standard things, and I create a listener and I parse it. And once I have like complete object of request object, I can do some blocking code here. That's not so bad. It's still nicer to make everything blocking, but if that's not feasible, this will still be okay with slow network connections because it's only blocking when it has the input, and then it can just do stuff, and that's okay in a blocking thread. But as long as you don't have to wait for that socket. So another aspect of RxJava, what I think is really powerful, is making APIs observable. So, for example, I have this method. That's an API to get the temperature in a city, and it goes to some HTTP client, and it returns XML. That you parse it, you get some value, and I don't know if you can read it down here, and then you can just call it, and you have a simple blocking thing, just like the one we started with. That's a blocking API. How can we make this non-blocking? Well, we can start by wrapping it in an observable. Now, what I do here is this code is all completely the same as it was before, but I'm making a pipe with just one item. So this is still, I'm just doing exactly the same thing, but I wrap it in a pipe. So now my API says that it returns an observable. So does that mean that you can simply wrap code into observable and then it's non-blocking? No, no. So, because this is what the client needs to do. It needs to do, you call it, then you have an observable. Then you have to say to blocking if you just want it in a blocking way. And in this case, the first, because there's only one. So that's still very much blocking code, and then you can do something with that value. But there is a very important improvement we have now. Because now the producer of the API and the consumer are independent of threading, right? Now you can start working on making one side or both sides non-blocking independently. So that might look something like this. Yeah. So that might look something like this. So for example, if the provider of the API here uses a non-blocking HTTP reader, it can start doing this and use just the primitive we talked about before, and this will have different threading, but the consumer, it won't break the consumer. If the consumer does still do blocking, it's still blocking in the end, but you can start focusing on the places where there's a lot of blocking, and you can start improving incrementally, and that's really nice. If the client also can use non-blocking code, so for example, you observe, you subscribe here and you use the whole non-blocking flow, now the whole thing is non-blocking. Now if this call takes 10 seconds, you don't waste the thread for 10 seconds, and that's huge. So if you have both them, if both are non-blocking, then you get your big payout basically. So this is also an interesting one, if I would add a cache to this. And the funny thing is, what I do first, suppose there's some map with temperatures or something, doesn't really matter. But if I have it in the cache, I just use blocking code to return it immediately as a static observable. If not, I go do I schedule it in a separate thread with the non-blocking and return, etc. This is actually kind of interesting because this part is blocking and this part is not. Because if you don't need to go anywhere and have I/O to remote systems, blocking is actually faster than non-blocking. Because scheduling things on different threads takes time. If you don't need to, if you have just it in local memory, this will be much faster to do it in the same thread. So now we have a situation that in this case, the data depends on, the threading depends on what data you have. If it's a cache hit, it will be the same thread that does everything. So what's also nice about RxJava, I think, it's not a new language. It's nothing fancy. It's just a library. It's not a framework, and you can just add it to your project and just start somewhere, improving your flow. And actually, for the servlet part, you need a pretty recent servlet engine, but nothing fancy. And Java 8 makes life a whole lot nicer, but it actually runs from Java 6. Yeah, so it is actually quite nice if you want to, if you have people in charge that are kind of reluctant to start with new kind of libraries and projects. You can just sell it as a very simple library like Apache Commons or something, and you can start without having to go through a lot of hoops to prove its worth beforehand. So it's not all rainbows and unicorns. There are some downsides. This is actually quite a big thing that people don't realize, that if threads are not an issue, if you have enough threads for whatever you want to do, it will perform the same, basically. Because if you have like a system that will have 10 connections, and the system is okay with having 10 threads doing that, it will perform the same way. It's not like you make a non-blocking, now everything is faster. It doesn't really work that way. Backpressure. So if we have a pipeline, if you visualize all the parts that are in the pipeline, every part, because it's a pushing pipeline, can perform their task at different speeds. Well, that can get you into some interesting problems, because if one part is really fast and the next part is really slow, somehow, if that goes on, it gets like a huge bubble of data somewhere, so to prevent that, all the different components in the pipe need to kind of communicate back, like saying, oh, slow down a little bit, speed up, slow down, because then you have a nice flowing pipe. If there is a place where it all builds up, you can have a small bug in your code, and that will blow up your whole VM because it eats up all the memory in seconds. So that's one of the other problems. Memory consumption might be much better if you get it right. It might be much, much worse if you get it wrong. So that's a bit interesting. Finally, I skipped some things because of time. I removed everything about error handling. It's really important, it's really nice, but not today. Scheduling, you can schedule a lot of different threads. No time for that. And the rest is also not really interesting. So I think if I look at the big picture, if you want to move a software system forward, you have to be able to do it incrementally. Not just say, okay, you throw everything away and you start new. That's not going to cut it anymore. So I think projects like this, where you can just start with something small in one corner, and until you're proficient and you do more and more, and that's a much more powerful way of making headway. So it's a beautiful thing to work with. I've had a lot of fun with it, so I think you should try it. And that's about all I've got. So, any questions? Silence. Yes! That was a close one.
Hello, thank you. It was a very good presentation. I liked it a lot. I would like to ask, at the start you said that there is one problem maybe. If you have some asynchronous requests, there is a question how often you can call these requests because you only get this OK response, and if RxJava solves this in any way.
Well, that's basically the backpressure thing. So there's a kind of invisible back channel that will, that way the pipe parts communicate with each other how fast they should go.
Okay, so basically you need to maintain it in your application.
Yeah, it's not free. I mean, if it's there are many situations where it's pretty straightforward. But if you have a part that will just start spitting out data at an insane rate, then you somehow need to deal with that. There's not something you can magically solve. So it depends.
Thank you.
Yes.
Thank you for your presentation again.
Thank you.
Just maybe general question. Is it possible to apply this RxJava approach to create a non-blocking REST API? And maybe you can advise any frameworks or libraries to do this.
Yes, there are many frameworks. I mean, if you want to do a new non-blocking REST API, you can use something like Akka or a Redpack. There are some really nice frameworks on top of this. What I wanted to do here is show that you can do it without a fancy framework and that you can just bolt it into the servlet. So yes, there are many. And I would say something like Redpack or Akka.
But within RxJava, there is no any for REST, directly for REST, some stuff.
Maybe. I don't know. Probably.
Okay, thank you.
You can use Rx and Redpack, I hear from some mysterious voice. All right, anybody else? Oh, there's somebody.
One more question. Is there any way to cancel pipeline processing? For example, I decided just to cancel it. I know that I don't need it more.
Yeah, so that's basically an unsubscribe. So like where we had the take operator and the just, at the example, what the take does after the 10 items, it says it cancels the pipeline. So you can do an unsubscribe on the whole thing and it will just stop.
Thank you.
Anybody else? Then thank you very much.